Hello, guys, welcome to a new chapter of the future of humanity. Today, we're going to be talking about Chapter 8 Building a Starship. In the movie Passengers, the Avalon, a state of the art starship powered by massive fusion engines, is traveling to Homestead 2, a colony on a distant planet. The ads for this settlement are alluring. The Earth is old, tired, overpopulated, and polluted. Why not make a fresh start in an exciting world? The journey takes 120 years, during which passengers are placed in suspended animation, their bodies frozen in pods. When the Avalon reaches its destination, the ship will automatically awaken its 5,000 riders. They will arise from their pods feeling refreshed and ready to build a new life in a new home. However, during the trip, a meteor storm punctures the ship's hull and damages its fusion engines, causing a cascade of malfunctions. One of the passengers is revived prematurely, with 90 years left to go in the voyage. He becomes lonely and depressed by the thought that the ship will not land until long after he is dead. Desperate for companionship, he decides to wake up a beautiful fellow traveler. Naturally, they fall in love, but when she finds out that he deliberately roused her almost a century too soon and that she too will die in interplanetary purgatory, she goes ballistic. Movies like Passengers embody recent attempts by Hollywood to inject a little realism into its science fiction. The Avalon makes its trip the old-fashioned way, never exceeding the speed of light. But ask any kid to imagine a starship and he or she will come up with something from the Enterprise like a Star Trek or the Millennium Falcon from Star Wars, capable of whisking crews across the galaxy at a faster than light clip, and perhaps even tunneling through space-time and zapping across hyperspace. Realistically, our first starship may not be manned and may not resemble any of the huge, sleek vehicles dreamed up in films. In fact, they may be no bigger than a postage stamp. In 2016, my colleague Stephen Hawking startled the world by backing a project called Breakthrough Starshot, which seeks to develop nanoships, sophisticated chips placed on sails energized by a huge bank of powerful laser beams on Earth, and the chips will each be the size of your thumb, weigh less than an ounce, and contain billions of transistors. One of the most promising aspects of the endeavor is that we can use existing technology to make it happen instead of having to wait 100 or 200 years. Hawking claimed that nanoships could be developed for 10 billion in the span of one generation, using 100 billion watts of laser power, will be able to travel at 1/5 the speed of light to reach the Centauri system, the nearest star system, in 20 years. By contrast, remember that each space shuttle mission remaining in Earth orbit almost cost $1 billion per launch. Nanoships will be able to accomplish what chemical rockets never can. Tsiolkovsky's rocket equation shows that it is impossible for a conventional Saturn rocket to reach the nearest star, since it will need exponentially more fuel the faster it went, and a chemical rocket simply cannot carry enough fuel for a journey of such length. Assuming it could reach the nearby stars, the trip will take about 70,000 years. Most of the energy of a chemical rocket goes into lifting its own weight into space, but a nanoship passively receives its energy from external ground beam lasers, and there is no wasted fuel. 100% of it goes into propelling the ship, and since nanoships do not need to generate their own energy, they have no moving parts. This significantly reduces the chances of mechanical breakdown. They also have no explosive chemicals and will not blow up on the launch pad or in space. Computer technology has advanced to the stage where we can pack an entire scientific laboratory into a chip. Nanoships will contain cameras, sensors, chemical kits, and solar cells, all designed to make detailed analysis of faraway planets and radio information back to Earth. Because the cost of computer chips has dropped dramatically, we could send thousands of them to the stars in the hope that a few of them might survive the hazardous journey. A nanoship whizzing by the Centauri system at 20% the speed of light will have just a few hours to complete its mission. In that time frame, it will locate Earth-like planets and rapidly photograph and analyze them to determine their surface characteristics, temperatures, and the composition of their atmospheres, in particular looking for the presence of water or oxygen. It will also scan the star system for radio emissions which might indicate the existence of alien intelligence. Mark Zuckerberg, founder of Facebook, has publicly supported breakthrough Starshot, and Russian investor and former physicist Yuri Milner has personally pledged $100 million. Nanoships are already much more than an idea, but there are several obstacles we must reckon with before we can fully execute this project. To send a fleet of nanoships to Alpha Centauri, a laser bank will have to fire a barrage of beams totaling at least 100 gigawatts at the parachutes of the ships for about 2 minutes. The light pressure from these laser beams will send the ships darting into space. The beams must be aimed with astonishing precision to ensure that the ships hit their target. The slightest deviation in their trajectory will compromise the mission. The main hurdle we face is not the basic science, which is already available, but funding, even with several high-profile scientists and entrepreneurs on board. Each nuclear power plant costs several $1 billion and can generate only 1 gigawatt or 1 billion watts of power. The process of soliciting federal and private financing for a sufficiently powerful and accurate laser bank is causing a severe bottleneck. As a practice run before aiming for distant stars, scientists may decide to send nanoships to closer destinations within the solar system. It will take them only 5 seconds to zip to the moon, about an hour and a half to get to Mars, and a few days to reach Pluto. Rather than waiting 10 years for a mission to the other planets, we could receive new information about them from nanoships in a matter of days, and in this way we could observe the developments in the solar system very nearly in real time. In a subsequent phase of the project, we might attempt to set up a battery of laser cannons to the moon. When a laser passes through the Earth's atmosphere, about 60% of its energy is lost. A lunar launch facility will help to remedy this problem, and solar panels on the moon could provide cheap and plentiful electrical energy to fuel the laser beams. Recall that one lunar day is equivalent to about 30 Earth days, so the energy could be efficiently collected and stored in batteries. The system will save us billions of dollars because, unlike nuclear power, sunlight is free. By the early 22nd century, the technology for self-replicating robots should be perfected, and we may be able to entrust machines with the task of constructing solar arrays and laser batteries on the moon, Mars, and beyond. We will ship over an initial team of automatons, some of which will mine the regolith and others of which will build a factory. Another set of robots can oversee the sorting, milling and smelting of raw materials in the factory to separate and obtain various metals. These purified metals could then be used to assemble laser launch stations and new batches of self-replicating robots. We might eventually have a bustling network of relay stations throughout the solar system, perhaps stretching from the moon all the way to the Oort cloud. Because the comets in the Oort cloud extend roughly halfway to Alpha Centauri and are largely stationary, they may be ideal locations for laser banks that could provide an extra boost to nanoships on their journey to our neighboring star system. As each nanoship passes on one of these relay stations, their lasers will fire automatically and give the ship an added push to the stars. Self-replicating robots could build this distant outpost by using fusion instead of sunlight as the basic energy source. Laser-propelled nanoships are used one type in a much larger category of starships called light sails. Just as sailboats capture the force of the wind, light sails harness the light pressure from sunlight or lasers. In fact, many of the equations used to guide sailboats can also be applied to light sails in outer space. Light is made up of particles called protons, and when protons strike an object, they do exert a minuscule pressure. Because light pressure is so small, scientists were not aware of its existence for a long time. It was Johannes Kepler who first noticed the effect when he realized that, contrary to expectations, comet tails always point away from the sun. Kepler correctly surmised that pressure from sunlight creates these tails by blowing dust and ice crystals in comets away from the sun. The prescient Jules Verne anticipated light sails from the Earth to the moon when he wrote, "There will someday appear velocities far greater than this, of which light or electricity will probably be the mechanical agent. We shall one day travel to the moon, the planets and the stars." Tsiolkovsky further developed the concept of solar sails or spaceships that utilize light pressure from the sun, but the history of solar sails has been spotty. NASA has not made them a priority. The Planetary Society's Cosmos 1 in 2005 and NASA's NanoSail D in 2008 both suffered launch failures. They were followed by NASA's nanosail D2, which entered low Earth orbit in 2010. The only successful attempt to send a solar sail past Earth orbit was accomplished by the Japanese in 2010. The Icarus satellite deployed a sail that was 46 feet by 46 feet in size and was powered by solar light pressure. It reached Venus in 6 months, thereby proving that solar sails were feasible. The idea continues to percolate despite its erratic progress. The European Space Agency is considering launching the Gossamer solar sail, whose purpose will be to deorbit some of the thousands of pieces of satellite junk littering the area around Earth. I recently interviewed Geoffrey Landis, an MIT-educated NASA scientist working on the Mars program as well as on light sails. Both he and his wife, Mari Tursillo, are award-winning science fiction novelists. I asked him how he managed to bridge such different worlds, one populated by meticulous scientists and their complex equations, the other filled with space groupies and UFO buffs. He responded that science fiction was wonderful because it allowed him to speculate far into the future. Physics, he said, kept him grounded. Landis' specialization is the light sail. He has proposed a starship for the journey to Alpha Centauri that will consist of a light sail made of an ultra-thin layer of a diamond-like material several hundred miles across. The ship will be gigantic, weighing 1 million tons, and will require resources from across the solar system to build and operate, including energy from laser banks near Mercury. To be able to stop at its destination, the ship will contain a large magnetic parachute with the field produced by a loop of wire 60 miles in diameter. Hydrogen atoms from space will pass through the loop and generate friction, which will gradually slow down the light sail over several decades. A round trip to Alpha Centauri and back will take 2 centuries, so the crew will have to be multi-generational. Although this starship is physically achievable, it will be costly, and Landis considered that it might take 50 to 100 years to actually assemble and test. In the meantime, he's helping to build the breakthrough Starshot laser sail. In addition to laser propulsion and solar sails, there are a number of other potential ways to energize a starship. To compare them, it is useful to introduce a concept called a specific impulse, which is the thrust of the rocket multiplied by the time over which the rocket fires. The longer a rocket fires its engines, the larger its specific impulse, from which its final velocity can be calculated. Here is a simple chart that ranks the specific impulse of several rockets. I have not included some designs like the laser rocket, solar sail and ramjet fusion rocket. As it is mentioned in the table, we have solid fuel rockets, liquid fuel rockets, nuclear fusion rockets, all the way to innovative concepts like the Antimatter Rockets, which will have a specific impulse between 1 million to 10 million. Notice that chemical rockets, which can only burn for a few minutes, have by far the lowest specific impulse, 250. Next on the list with the ion engines, they are very useful for missions to nearby planets. They start by taking a gas like xenon, stripping the electrons from its atoms to turn them into ions, and then accelerating these ions with an electric field. The inside of an ion engine bears some resemblance to the inside of a TV monitor, where electric and magnetic fields guide beams of electrons. The thrust of ion engines is so excruciatingly small, often measured in ounces, that when you turn on one in the lab, nothing seems to happen. But once in space, over time they can attain velocities exceeding chemical rockets. Ion engines have been compared to the tortoise in the race with the hare, which in this case will be chemical rockets. Although the hare can sprint with enormous speed, it can only do so for a few minutes before it is exhausted. The tortoise, on the other hand, is slower but can walk for days and thus wins long-distance competitions. Ion rockets can operate for years at a time and hence have considerably larger specific impulses than chemical rockets. To increase the power of an ion engine, one might ionize the gas using microwaves or radio waves, and then use magnetic fields to accelerate the ions. This is called a plasma engine, which in theory could cut the travel time to Mars from 9 months to fewer than 40 days according to its proponents, but the technology is still in development. One of its main limiting factors is the large amount of electricity necessary to create the plasma, which may even require a nuclear power plant for interplanetary missions. NASA has studied and built ion engines for decades. For example, the deep space transport, which may take our astronauts to Mars in the 2030s, uses ion propulsion. Late in this century, ion engines will most likely become the backbone of interplanetary space missions. Although chemical rockets, which might still be the best option for time-sensitive missions, ion engines will be a solid, dependable choice when time is not the most important consideration. In 2011, DARPA and NASA funded a symposium entitled The 100-Year Starship. It generated considerable interest. The aim was not to build an actual starship within 100 years, but to assemble top scientific minds who could lay out a feasible agenda for interstellar travel for the next century. The project was organized by members of the Old Guard, an informal group of elderly physicists and engineers, many now in their 70s, who seek to draw upon their collective knowledge to take us to the stars. They have passionately kept the flame alive for decades. Landis is a member of the Old Guard, but there is also a unusual pair among them, James and Gregory Beckford, twins who happen to both be physicists as well as science fiction writers. James told me that his fascination with the starships began when he was a child, devouring all the science fiction he could get his hands on, especially Robert Heinlein's old Space Cadet series. He realized that if he and his brother were serious about space, they would have to learn physics, lots of it. So both set off to get their PhDs in their field. James is now the president of Microwave Sciences and has worked for many decades with high-power microwave systems. Gregory is a professor of physics at the University of California, Irvine, and in his other life has won the coveted Nebula Award for one of his novels. In the wake of the 100-Year Starship Symposium, James and Gregory wrote a book, Starship Century Towards the Grandest Horizon, containing many of the ideas presented there. James, an expert on microwave radiation, believes that light sails are our best chance of travel beyond the solar system, but he said that there is a long history of alternate theoretical designs that will be exceedingly expensive, but are based on solid physics and might one day actually happen. The history of nuclear rockets goes back to the 1950s, an era when most people lived in terror of nuclear war, but a few atomic scientists were looking for peaceful application of nuclear energy. They considered all sorts of ideas, such as deploying nuclear weapons to carve out ports and harbors. Most of these suggestions were rejected due to concerns about the fallout and disruption from nuclear explosions. One intriguing proposal that lingered, however, was called Project Orion, and it sought to use nuclear bombs as the power source for starships. The skeleton of the plan was simple: create mini atomic bombs and eject them one by one from the back end of a starship. Each time a mini nuke exploded, it would create a shockwave of energy that would push the starship forward. In principle, if a series of mini nukes were released in succession, the rocket could accelerate to nearly the speed of light. The idea was developed by nuclear physicist Ted Taylor along with Freeman Dyson. Taylor was famous for designing a wide variety of nuclear bombs, from the largest fusion bomb ever detonated, with a force of about 25 times the Hiroshima bomb, down to the Little Davy Crockett portable nuclear cannon, with a force of 1,000 times smaller than the Hiroshima bomb. But he longed to channel his extensive knowledge of nuclear explosives towards peaceful purposes. He jumped at the opportunity to pioneer the Orion Starship. The main challenge was figuring out how to carefully control the sequence of small detonations so that the Starship could safely ride the wave of nuclear blast without being destroyed in the process. Different designs for a range of speeds were drawn up. The largest model will be a quarter of a mile in diameter, will weigh 8 million metric tons and will be propelled by 1,080 bombs. On paper, it could attain a velocity of 10% of the speed of light and reach Alpha Centauri in 40 years. Despite the immense size of its ship, calculations showed that it just might work. Critics converge on the idea, however, pointing out that nuclear pulse starships would unleash radioactive fallout. Taylor countered that fallout is created when dirt and the metallic bomb casing become radioactive after the bomb is set off, so it could be avoided if the starship only fired its engine in outer space. But the Test Ban Treaty of 1963 also made it difficult to experiment with miniature atomic bombs. The Orion Starship ultimately wound up as a curiosity relegated to old science books. Another reason the project came to a close was that Ted Taylor himself lost interest. I once asked him why he withdrew his support for the effort, since it seemed like a natural use for his talent. He explained to me that to create the Orion would be a produce of a new type of nuclear bomb. Although he spent most of his life designing uranium fission bombs, he realized that one day the Orion spacecraft might use powerful, especially designed hydrogen bombs as well. These bombs, which release the greatest amount of energy known to science, have gone through 3 stages of development. The first hydrogen bombs of the 1950s were gigantic devices that required large ships to transport them. For all purposes, they would have been useless in a nuclear war. Second generation nuclear bombs are the small portables MIRVs, or multiple independently targetable re-entry vehicles, that make up the backbone of the US and Russian nuclear arsenals. You can pack 10 of them into the nose cone of an intercontinental ballistic missile. Third generation nuclear bombs, sometimes called designer nuclear bombs, are at the moment still a concept. They will be easily concealed and custom made for specific battlefields. Taylor told me that he had become disillusioned with the project and feared that terrorists could get hold of them. It would be an unspeakable nightmare for him if his bombs fell into the wrong hands and destroyed an American city. He reflected candidly on the irony of his about face. He had contributed to a field in which scientists would put pins, each representing a nuclear bomb, in a map of Moscow, but when faced with the possibility that third-generation weapons could put pins in an American city, he suddenly decided to oppose the development of advanced nuclear weapons. James Benford informed me that although Taylor's nuclear pulse rocket never made it out of the drawing board, the government actually did produce a series of nuclear rockets. Instead of exploding mini-atomic bombs, these rockets used an old-fashioned uranium reactor to generate the necessary heat. It was used to heat up a liquid such as liquid hydrogen to a high temperature and then shoot it out a nozzle in the back, creating thrust. Several versions were built out and tested in the desert. These reactors were quite radioactive and there was always the danger of a meltdown during the launch phase, which would have been disastrous. Due to an assortment of technical problems as well as growing anti-nuclear sentiment among the public, these nuclear rockets were mothballed. The scheme to employ nuclear bombs to propel starships died in the 1960s, but in the wings was another possibility. In 1978, the British Interplanetary Society initiated Project Daedalus. Instead of using uranium fission bombs, Daedalus would use mini-hydrogen bombs, which Taylor himself looked at but never developed. There are several ways in which to release the power of fusion peacefully. One process called magnetic confinement involves placing hydrogen gas in a larger magnetic field the shape of a donut and then heating it to a million degrees. Hydrogen nuclei smash into one another and are fused into helium nuclei, releasing bursts of nuclear energy. The fusion reactor can be used to heat up a liquid, which is then released through a nozzle, thereby propelling the rocket. The leading fusion reactor using magnetic confinement at present is called the International Thermonuclear Experimental Reactor, located in southern France. It is a monstrous machine, 10 times larger than its closest competitor. It weighs more than 5,000 tons, stands 37 feet tall and 64 feet in diameter, and has cost more than $14 billion so far. It is expected to attain fusion by 2035 and ultimately produce 500 megawatts of heat energy. It is hoped that it will be the first fusion reactor to generate more energy than it consumes. Despite a series of delays and cost overruns, physicists I have talked to are betting that the ITER reactor will make history. We will have our answer before too long. As Nobel laureate Pierre Gilles de Gennes once said, we say that we will put the sun into a box. The idea is pretty. The problem is we don't know how to make the box. Another variation of the Daedalus rocket might be fueled by laser fusion, in which giant laser beams compress a pellet of hydrogen-rich material. This process is called inertial confinement. The National Ignition Facility based at the Livermore National Laboratory in California exemplifies this process. Its battery of lasers, 192 gigantic laser beams in 4,900-foot-long tubes, is the largest in the world. When the laser beams are focused on a tiny sample of hydrogen-rich lithium deuteride, their energy incinerates the surface of the material, resulting in a mini-explosion that causes the pellet to collapse and raise its temperature to 100 million degrees Celsius. This creates a fusion reaction that unleashes 500 trillion watts of power in a few trillionths of a second. I saw a demonstration of the NIF while hosting a Discovery Science Channel documentary. Visitors must first pass a series of national security checks because the US nuclear arsenal is designed at the Livermore laboratory. When I finally entered, it was overwhelming. A 5-story apartment building could easily fit into the main chamber where the laser beams converge. One version of Project Daedalus exploits a process similar to laser fusion. Instead of a laser beam, it uses a large bank of electron beams to hit the hydrogen-rich pellet. If 250 pellets are detonated per second, enough energy could conceivably be generated for a Starship to reach a fraction of the speed of light. However, this design would require a fusion rocket of truly immense size. One version of the Daedalus rocket would weigh 54,000 metric tons and will be about 625 feet long, with a maximum velocity of 12% of the speed of light. It is so big it would have been to be constructed in outer space. The nuclear fusion rocket is conceptually sound, but fusion power has not yet been demonstrated. Furthermore, the sheer size and complexity of these project rockets cast doubt on their feasibility, at least in this century. Still, alongside the light sail, the fusion rocket holds the most promise. Fifth-wave technologies, which include antimatter engines, light sails, fusion engines, and nanoships, may open up exhilarating new horizons for Starship design. Antimatter engines, as in Star Trek, may become a reality. They would utilize the greatest energy source in the universe, the direct conversion of matter into energy through matter and antimatter collisions. Antimatter is the opposite of matter, meaning that it has the opposite charge. An anti-electron has a positive charge, while an antiproton has a negative charge. When matter and antimatter collide, both are annihilated into pure energy, so the reaction releases energy with 100% efficiency. A nuclear weapon, by contrast, is only 1% efficient. Most of the energy inside a hydrogen bomb is wasted. An antimatter rocket will be rather simple in design. The antimatter will be stored in secure containers and fed into a chamber in steady streams. It will combine explosively with ordinary matter in the chamber and result in a burst of gamma rays and X-rays. The energy will then be shot through an opening in the exhaust chamber to create thrust. As James Benford remarked to me, antimatter rockets are a favorite concept among science fiction fans, but there are serious problems with building them. For one matter, antimatter is naturally occurring but only in relatively small quantities, so we'll have to manufacture large amounts for its use in engines. The first anti-hydrogen atom with an anti-electron circling around an antiproton was created in 1995 at the European Organization for Nuclear Research in Geneva, Switzerland. A beam of ordinary protons was produced and shot through a target made of ordinary matter. The collision resulted in a few particles of antiprotons. Huge magnetic fields separated the protons from the antiprotons by driving them in different directions, one bending to the right and the other one to the left. The antiprotons were then slowed down and stored in a magnetic trap, where they were combined with anti-electrons to form antihydrogen. In 2016, physicists at CERN took antihydrogen and analyzed the anti-electron shells that orbit the antiproton. As expected, they found an exact correspondence between the energy levels of antihydrogen and ordinary hydrogen. CERN scientists have announced that if we could assemble all the antimatter we have made at CERN, annihilated with matter, we will have enough energy to light a single electric bulb for a few minutes. A whole lot more would be needed for a rocket. Also, antimatter is the most expensive form of matter known to the world. As of today's prices, a gram will go for about $70 trillion. Currently, it can only be created in very small amounts with particle accelerators, which are extremely costly to construct and operate. The Large Hadron Collider at CERN is the most powerful particle accelerator in the world and costs more than $10 billion to set up, but it can only produce a very thin beam of antimatter. It will bankrupt the United States to accumulate enough fuel. The giant atom smashers of today are all-purpose machines, used purely as research tools and are highly inefficient in their production of antimatter. One partial solution might be to establish factories specially designed to churn it out. In that case, Harold Gernish of NASA believes that the cost of antimatter could go down to $5 billion per gram. Storage presents another difficulty and expense. If you put antimatter in a bottle, sooner or later it will hit the walls of the bottle and annihilate the container. Penning traps will be needed to enclose it properly. These traps would use magnetic fields to hold atoms of antimatter in suspension and prevent them from coming into contact with the vessel. In science fiction, issues of cost and storage are sometimes eliminated by the discovery of a deus ex machina, an anti-asteroid that enables us to mine antimatter cheaply, but this hypothetical scenario raises a complicated question. Where does antimatter come from anyway? Everywhere we look in outer space with our instruments, we see matter, not antimatter. We know this because the collisions of one electron with an anti-electron releases a minimum energy of 1.2 million electron volts. This is the fingerprint of an antimatter collision, but when we examine the universe, we detect very little of this type of radiation. Most of the universe we see around us is made of the same ordinary matter we are made of. Physicists believe that at the instant of the Big Bang, the universe was in perfect symmetry and there was an equal amount of matter and antimatter. If so, the annihilation between the two would have been perfect and complete, and the universe should be made of pure radiation. Yet, here we are, made of matter which should not be around anymore. Our very existence defies modern physics. We have not yet figured out why there is more matter than antimatter in the universe. Only 1/10 billion of the original matter in the early universe survived this explosion, and we are part of it. The leading theory is that something violated the perfect symmetry between matter and antimatter at the Big Bang, but we don't know what it is. There is a Nobel Prize waiting for the enterprising individual who can solve this problem. Antimatter engines are on the short list of priorities for anyone who wants to build a starship, but the properties of antimatter are still almost totally unexplored. It is not known, for example, whether it falls up or down. Modern physics predicts that it should fall down like ordinary matter. If so, then anti-gravity will probably not be possible. However, this, along with so much else, has never been tested. Based on cost and our limited understanding, antimatter rockets will probably remain a dream for the next century unless we happen to run into an anti-asteroid drifting in space. The ramjet fusion rocket is another exciting concept. It will look like a giant ice cream cone and will scoop up hydrogen gas in interstellar space, then concentrate it in a fusion reactor to generate energy. Like a jet or a cruise missile, the ramjet rocket will be quite economical. Because jets gulp ordinary air, they do not have to carry their own oxidizer, which reduces cost. Since there is an unlimited amount of hydrogen gas in space for fuel, the spaceship should be able to accelerate forever. As with the solar sail, the engine's specific impulse is infinite. The famous novel Tau Zero by Paul Anderson is about a ramjet fusion rocket that suffers a malfunction and cannot shut down. As it accelerates towards the speed of light, bizarre relativistic distortions begin to occur. Time slows down within the rocket, but the universe around it ages as usual. The faster it goes, the slower time beats inside it. To someone on the starship, however, things seem perfectly normal inside, while the universe outside ages rapidly. Eventually, the starship goes so fast that millions of years pass outside the ship as the crew members watch helplessly. After traveling uncounted billions of years into the future, the crew realizes that the universe is no longer expanding, but is actually shrinking. The expansion of the universe is finally reversing. The temperature soars as the galaxies begin to come towards the final big crunch. At the end of the story, just as all the stars are collapsing, the rocket manages to skip past the cosmic fireball and witness a Big Bang as a new universe is born. As fantastic as this tale might be, its foundations do conform to Einstein's theory of relativity. Apocalyptic narratives aside, the ramjet fusion engine at first might seem too good to be true, but over the years a number of possible criticisms have been leveled at it. The scoop might have to be hundreds of miles across, which will be both impractically large and prohibitively costly. The rate of fusion might not produce enough energy to sustain a starship. Dr. James Benson also pointed out to me that our sector of the solar system does not contain enough hydrogen to feed the engines, though perhaps other areas of the galaxy might. Others claim that the drag on a ramjet engine as it moves in the solar wind would exceed its thrust, so it could never reach relativistic velocities. Physicists have tried to modify the design to rectify these advantages, but we have a long way to go before ramjet rockets become a realistic option. It should be emphasized that all the starships mentioned so far face other problems associated with traveling near light speed. Asteroid collisions will present a major risk, and even tiny asteroids could pierce the hull of the ship. As we mentioned, the space shuttle suffered small nicks and scars from cosmic debris which probably hit the spacecraft near orbiting velocity. Near light speed, however, impacts will take place at many times that velocity, potentially pulverizing parts of the ship. In the movies, this hazard is eliminated by powerful force fields that conveniently repel all the micrometeorites. Both those unfortunately only exist in the minds of science fiction writers. In reality, electric and magnetic force fields can indeed be generated, but even household objects that are not charged, such as plastic, wood, and plaster, could easily penetrate them. In outer space, tiny micrometeorites, because their own charge cannot be deflected by electric and magnetic fields, and gravitational fields are attractive and extremely weak, so they will not be suitable for the repulsive force fields we will need. Braking is another challenge. If you're zipping through space at a velocity approaching light speed, how do you slow down when you reach your destination? Solar and laser sails depend on the energy of the sun or banks of laser beams, which cannot be used to decelerate the Starship, so they may be useful mainly in flyby missions. Perhaps the best way to brake nuclear rockets is to turn them around 180 degrees so the thrust is in the opposite direction. However, this strategy will consume roughly half of the mission's thrust to reach the target velocity and the other half to slow down the rocket. For solar sails, perhaps sails can be reversed so that light from the stars at the destination can be used to slow down the spacecraft. Another issue is that most of these starships capable of carrying astronauts will be hefty and could only be assembled in outer space. Scores of space missions will be required to send the building materials into orbit and still more to assemble the pieces. To avoid insurmountable expenses, a more economical method of launching missions into space must be devised. That is where the space elevator comes in. Space elevators will be a game-changing application of nanotechnology. A space elevator is a long shaft that stretches from the Earth into outer space. You will enter the elevator, press the up button, and then be rapidly lifted into orbit. You will then suffer the crushing G-forces experienced when a booster rocket blasts off its launch pad. Instead, your ride into space will be as mild as taking the elevator to the top of a department store. Like Jan's beanstalk, the space elevator will seemingly defy gravity and provide an effortless way to ascend into the skies. The possibility of a space elevator was first explored by the Russian physicist Konstantin Tsiolkovsky, who was intrigued by the building of the Eiffel Tower in the 1880s. If engineers could build such a magnificent structure, he asked himself, why not keep going and extend one into outer space? Using simple physics, he was able to show that in principle, if the tower was long enough, then centrifugal force will be sufficient to keep it upright, without any external force. Just as a ball on a string does not fall to the floor because of its spin, a space elevator will be kept from collapsing by the centrifugal force of the Earth. The notion that perhaps rockets were not the only way to enter space was radical and exciting, but there was an immediate roadblock. The stress on space elevator cables might reach 100 gigapascals of tension, which exceeds the breaking point of steel, which is 2 gigapascals. Steel cables would snap and the space elevator would come tumbling down. The concept of space elevators was shelved for almost 100 years. They were mentioned occasionally by authors like Arthur C. Clarke, but no one is laughing anymore. Suddenly, space elevators don't seem so far-fetched after all. In 1999, a preliminary NASA study assessed that an elevator with a cable 3 feet wide and 30,000 miles long could transport 15 tons of payload. In 2013, the International Academy of Astronautics issued a 350-page report projecting that with enough funding and research, a space elevator capable of carrying multiple 20-ton payloads might be possible by 2035. Price estimates usually range from 50 to 10 to 50 billion, a fraction of the $150 billion that went into the International Space Station. Meanwhile, space elevators could reduce the cost of putting payloads into space by a factor of 20. The problem is no longer one of the basic physics, but of engineering. Serious calculations are now being made to determine whether space elevator cables could be made of pure carbon nanotubes, which are so strong that they will not break. But can we make enough of these nanotubes to stretch thousands of miles into space? At present, the answer is no. Pure carbon nanotubes are extremely difficult to manufacture beyond a centimeter or so. You might hear announcements that the nanotubes many feet long have been constructed, but those materials are actually composites. They consist of tiny threads of pure carbon nanotubes compressed into a fiber and lose the wondrous properties of pure nanotubes. To stimulate interest in projects like the space elevator, NASA sponsors the Centennial Challenges program, which awards prizes to amateurs who can invent advanced technologies for the space program. It once held a contest calling for entrants to submit components for a mini elevator prototype. I participated in it for a TV special I hosted, following a group of young engineers who were convinced that space elevators would open up the heavens to the average person. I watched as they used laser beams to send a small capsule up a long cable. Our TV special tried to capture the enthusiasm of this new class of entrepreneurial engineers keen to build the future. Space elevators will revolutionize our access to outer space, which instead of remaining the exclusive territory of astronauts and military pilots, could become a playground for children and families. They would offer an efficient new approach to space travel and industry, and make possible the extraterrestrial assembly of complex machinery, including starships that could travel at the speed of light. But realistically, given the enormous engineering problems facing us, a space elevator might not be possible until late in this century. Of course, considering our restless curiosity and ambition as a species, we will eventually move on beyond fusion and antimatter rockets and face the greatest challenge of all. What is the possibility that one day we might break the ultimate speed limit in the universe, the speed of light? Warp drives. One day, a boy read a children's book and changed world history. It was 1895 and the cities were beginning to be wired up for electricity. To understand this strange new phenomenon, the boy picked up popular books on natural science by Aaron Bernstein. In it, the author asked readers to imagine riding alongside an electric current inside a telegraph wire. The boy then wondered what it would be like if you could replace the electric current with a beam of light. Can't you outrace light? He reasoned that since light was a wave, the light beam would look stationary, frozen in time. But even at the age of 16, he grasped what no one had done before. Finally, in 1905, he found the answer. His name was Albert Einstein, and his theory was called special relativity. He discovered that you cannot outrace a light beam because the speed of light is the ultimate velocity in the universe. If you approach it, strange things happen. Your rocket becomes heavier and time slows down inside it. If you were to somehow reach light speed, you will be infinitely heavy and time will stop. Both conditions are impossible, which means you cannot break the light barrier. Einstein became the cop on the block, setting the ultimate speed limit in the universe. This barrier has bedeviled generations of rocket scientists ever since. But Einstein was not satisfied. Relativity could explain many of the mysteries of light, but he wanted to apply his theory to gravity as well. In 1915, he came up with an astonishing explanation. He postulated that space and time, which were once thought to be inert and static, were actually dynamic, like smooth bedsheets that can be bent, stretched, or curved. According to his hypothesis, the Earth does not revolve around the Sun because it is pulled in by the Sun's gravity, but because the Sun warps the space around it. The fabric of space-time pushes on the Earth so that it moves in a curved path along the Sun. Simply put, gravity does not pull. Instead, space pushes. Shakespeare once said that all the world is a stage and we are actors making our entrances and exits. Picture space-time as an arena. It was once thought to be static and flat, absolute, with clocks ticking at the same rate across the surface. But in Einstein's universe, the stage can be warped. Clocks run at different rates. Actors cannot walk across the stage without falling over. They might claim that an invisible force is pulling them in from various directions, when actually the warp stage is pushing them. Einstein also realized that there was a loophole in his general theory of relativity. The larger a star is, the greater the warping of space-time surrounding it. If a star is heavy enough, it becomes a black hole. The fabric of space-time may actually tear, potentially creating a wormhole. With this concept introduced by Einstein and his student Nathan Rosen in 1935, it is called today the Einstein-Rosen bridge. Wormholes. The simplest example of an Einstein-Rosen bridge is the looking glass from Alice's Adventures in Wonderland. On one side of the looking glass is the countryside of Oxford, England, and on the other side is the fantasy world of Wonderland, to which Alice is instantly transported when she puts her finger through the glass. Wormholes are a favorite plot device in the movies. Han Solo sends the Millennium Falcon through hyperspace by propelling it through a wormhole. The refrigerator that Sigourney Weaver's character opens in Ghostbusters is a wormhole through which she peers at an entire new universe. Wormholes were discovered by analyzing the mathematics of black holes, which are collapsed giant stars whose gravity is so intense that even light cannot escape. Their escape velocity is the speed of light. In the past, black holes were thought to be stationary and to have infinite gravity and called a singularity, but all the black holes that have been recorded in space are spinning quite rapidly. In 1963, physicist Roy Kerr discovered that a spinning black hole, if it was moving fast enough, would not necessarily collapse to a pinpoint, but to a spinning ring. The ring is stable because centrifugal force prevents it from collapsing. So where does everything that falls into a black hole go? Physicists do not yet know, but one possibility is that matter can emerge from the other side through what is called a white hole. Scientists have looked for white holes which would release matter rather than swallow it up, but have not found any so far. If you approach the spinning ring of a black hole, you will witness incredible distortions of space and time. You might see light beams captured billions of years ago by the wormhole's gravity. You might even meet copies of yourself. Your atoms might be stretched by tidal forces in a disturbing and lethal process called spaghettification. If you enter the ring itself, you might be expelled through a white hole in a parallel universe on the other side. Imagine taking two sheets of paper held parallel to each other and then drilling a hole through them with a pencil to connect them. If you travel along the pencil, you will pass between two parallel universes. However, if you pass through the ring a second time, you will arrive at another parallel universe. Each time you went into the ring, you will reach a different universe, in the same way that entering an elevator allows you to move between different floors of an apartment building, except in this case you could never return to the same floor. Gravity will be finite as you enter the ring, so you will not necessarily be crushed to death. However, if the ring was not spinning fast enough, it could still collapse you and kill you. But it may be possible to stabilize the ring artificially by adding something called negative matter or negative energy. A stable wormhole is therefore a balancing act, and the key is to maintain the right mixture of positive and negative energy. You need lots of positive energy to naturally create a gateway between universes as with a black hole, but you also need to create negative energy to keep the gateway open and prevent the collapse. Negative energy is quite different from antimatter and has never been detected in nature. Negative energy has bizarre anti-gravitational properties, meaning that it will fall up rather than down. If it existed on the Earth billions of years ago, it would have been repelled by the matter of the planet and would have floated into outer space. Perhaps that's why we haven't found any. Although physicists have seen no evidence of negative matter, negative energy has actually been created in the laboratory. This keeps alive the hope of science fiction fans who one day dream of traveling through wormholes to distant stars. However, the amount of negative energy that has been created in the laboratory is minuscule, far too small to drive a starship. To create enough negative energy to stabilize a wormhole would require an extremely advanced technology. So for the foreseeable future, hyperdrive wormhole starships are beyond our capacity. But recently there has been some excitement generated by another means to warp space and time. In addition to wormholes, the Alcubierre engine might offer a second way to break the light barrier. I once interviewed the Mexican theoretical physicist Miguel Alcubierre. He was struck with the groundbreaking idea in relativistic physics while watching TV. Perhaps the first time this has ever happened. During an episode of Star Trek, he marveled that the Starship Enterprise could travel faster than light. It could somehow compress the space in front of it so that the stars did not seem as distant. The Enterprise did not journey to the stars came to the Enterprise. Think of moving across a carpet to reach a table. The common sense way is to walk along the carpet from one way to another, but there is another way. One could rope the table and drag it towards you so that you are compressing the carpet. So instead of walking across the carpet to reach the carpet folds up and the table comes to you. An interesting realization dawned on him. Usually you start with a star or planet and then use Einstein's equations to calculate the bending of space around it. But you can also go backwards. You can identify a particular warping and use the same equation to determine the type of star or planet that will cause it. A rough analogy might be made to the way an auto mechanic builds a car. You could begin with the parts that are available and assemble a car from them, or you could select the design of your dreams and then figure out the parts necessary to do it. Alcubierre turned Einstein's math on its head, reversing the usual logic of theoretical physicists. He attempted to gauge what kind of a star might compress space in the forward direction and expand it in the backward direction. Much to his shock, he reached a very simple answer. It turned out that the space warp used in Star Trek was an allowed solution of Einstein's equations. Perhaps warp drive was not so improbable after all. A starship equipped with an Alcubierre drive would have to be surrounded by a warp bubble, a hollow bubble of matter and energy. Space-time inside and outside the bubble would be disconnected. As the starship accelerated, people inside it would feel nothing. They might not think that the ship was moving at all, even though they would be traveling faster than light. Alcubierre's result shocked the physics community because it was so novel and radical, but after his paper was published, critics began to point out its weak spots. Although its vision for faster than light travel was elegant, it did not address all the complication. If the region inside the starship is separated from the outside world by the bubble, information will not be able to get through, and the pilot will not be able to control the direction of the ship. Steering will be impossible, and then there is the issue of actually creating a warp bubble. In order to compress the space in front of it, it will have to have a certain kind of fuel, that is negative matter or energy. We are right back to where we started. Negative matter or negative energy will be the missing ingredient needed to keep our warp bubble as well as our wormholes intact. Stephen Hawking has proven a general theorem stating that all solutions of Einstein equations that allow faster than light travel must involve negative matters of energy. In other words, positive matter and energy that we see in stars can warp space and time so that it perfectly describes the motion of heavenly bodies, but negative matter and energy warp space and time in bizarre ways, creating an anti-gravitational force that can stabilize wormholes and prevent them from collapsing and propel warp bubbles to faster than light velocities by compressing space and time in front of them. Physicists have tried to calculate the amount of energy matter necessary to propel a starship. The latest results indicate that the amount required is equivalent to the mass of Jupiter. This means that only a very advanced civilization will be able to use negative matter or energy to propel their starships if possible at all. Star Trek goes around this inconvenient hurdle by postulating that a rare mineral called dilithium crystal is the essential component of a warp drive engine. Now we know that dilithium crystals may be a fancy way of saying negative matter. Dilithium crystals do not exist, but tantalizingly, negative energy does, leaving open the possibility of wormholes, compressed space, and even time machines. Although Newton's laws do not allow negative energy, quantum theory does through the Kashmir effect, which was proposed in 1948 and measured in the laboratory in 1997. Say that we have two parallel metal plates that are uncharged. When they are separated by a large distance, we say that there is zero electrical force between them, but as they get closer, they mysteriously begin to attract each other. We can then extract energy from them. Since we start with zero energy but obtain positive energy when the plates are brought together, it follows that the plates themselves originally had negative energy. The reason is rather esoteric. Common sense tells us that a vacuum is a state of emptiness, with zero energy, but actually it is teeming with matter and antimatter particles that materialize briefly out of the vacuum and then annihilate back into it. These virtual particles appear and disappear so rapidly that they do not violate the conservation of matter and energy. This constant churning in the vacuum creates pressure. Since there is more matter and antimatter activity outside the plates than between them, this pressure pushes the plates together, creating negative energy. This is the Kashmir effect, which in quantum theory demonstrates that negative energy can exist. Originally, because the Kashmir is such a tiny force, it could only be measured with the most sensitive equipment available, but nanotechnology has advanced to the point at which we can tinker with individual atoms. For a TV special I once hosted, I visited a laboratory at Harvard that had a small tabletop device that could manipulate atoms. In the experiment I observed, it was difficult to prevent two atoms that had been brought close to each other from flying apart or coming together due to the Kashmir force, which can either be repulsive or attractive. Negative energy may seem like the holy grail to a physicist building a starship, but for a nanotechnologist, the Kashmir force is so strong at the atomic level that it becomes a nuisance. In conclusion, negative energy does exist, and if enough negative energy could somehow be collected, we could in principle create a wormhole machine or a warp drive engine. fulfilling some of the wildest fantasies of science fiction, but these technologies are still a long way off. In the meantime, we will make do with the light sail that might be zooming through space by the end of the century, offering the first close-up pictures of exoplanets orbiting the stars. By the 22nd century, we may be able to visit these planets ourselves on fusion rockets, and if we can solve the intricate engineering problems in front of us, we may even be able to make antimatter engines, ramjet engines, and space elevators a reality. Once we have starships, what will we find in deep space? Will there be other worlds that can sustain humanity? Fortunately, our space telescopes and satellites have given us a detailed look at what lurks amongst the stars.